Hello and welcome to ST118 Statistics and Applications Session 2 Part 3. In this video, we would like to basically discuss about skewness. But before that, I would like to remind or maybe introduce this concept called Z value, and then we will proceed to talk about skewness. Okay, all right. So the idea of Z value and skewness, they are in a way quite related. That's why I want to first make you understand the concept of Z value. And before we start, let's recap what's the familiar example that we have been using, which is having 1, 2, 3, 4. So that's 4. And we have 5, 10, 15, 20. We have 3 counts of 5, 4 counts of 10, 2 counts of 15, and 1 count of 20. And again, we kept saying that for presentational purposes, sometimes we fatten it to a bar, we shade the body to give it more recognizable form, visual form, but the information is in the axis. Okay, so recall that earlier on we calculated the values of mu to be 10.5, right? X bar also was 10.5. Sigma was 4.717 and S was 4.9721. This was done step by step earlier on in our previous video. Sample size altogether n. So n here is taken as 10, n here is taken as 10. For the same set of data, if we treat it as population, if we treat it as sample. Of course, these two are mutually exclusive. We cannot choose the data to become the population because that would be very bizarre, right? If you cannot measure the population, just define the population. That's weird. So oftentimes, if we are already, we've already taken the measurements and they are supposed to be trying to estimate the bigger population mean or variance or other parameters, population parameters, then it's basically a sample. We're stuck with it. But here, just to understand the concepts, I'm reusing, all right, the same set of data. If treated as population, we get these numbers. The same data, if treated as sample, we get these numbers. So that was what was going on. Now, for Z value, let's jump in. The Z formula, first of all, for datum x is given by little z, which is calculated as x minus mu over sigma. So it is a very linear and simple formula. Basically like minusing the offset. Yeah, taking the population mean as the center, which is the center of gravity. So minusing the mean, which will result in either a plus or a minus numerator, right? And dividing by sigma, which is always positive. So if the datum is larger than the population mean, that means to the right of the population mean, then Z value will be positive. If the datum is smaller than the population mean, then Z value will be negative. So it's very telling, right? It reveals whether you are large or small relative to always the population mean. Okay, so what's the point of Z value? First of all, let's note that negative value, right, implies left of mu. Positive z value implies to the right of mu. And if we have a diagram like this, okay, using the summaries that we have earlier on, and it can be this histogram or some other shapes, such as this, okay, where the population mean is 10.5. And the standard deviation is 4.717. Yeah, okay. All right, so what is the significance here? Well, if we map it to the z value axis, yeah, the mean always becomes 0. The population mean always has, by definition, a z value of 0, because if you substitute mu into x, mu minus mu is 0, no matter what is your sigma, right? So the z value of mu is always 0. What is the z value of, let's say, 15.217? And you will notice that it is actually mu plus sigma, or mu plus 1 sigma, 1 times sigma is 15.217. Mu plus 1 sigma minus mu, that's 1 sigma. 1 sigma divided by sigma is 1, which means that we have a z value of plus 1. What about mu minus 1 sigma, which is, I think I'm getting 5.983, but you get the idea, right? So mu minus 1 sigma. What's the z value of 5.983? Mu minus 1 sigma minus mu. So that's minus 1 sigma in the numerator. Divide by sigma, that's minus 1. Just the value minus 1. So which means the z value of mu minus 1 sigma is minus 1. Now, did you see a pattern there? This is mu plus 1 sigma, mu minus 1 sigma. Of course, you will ask, what's the z value of mu plus 2 sigma, mu plus 3 sigma, mu minus 2 sigma, mu minus 3 sigma, right? And yes, not surprisingly, mu plus 2 sigma always maps to plus 2. Mu plus 3 sigma always maps to plus 3 as the z value. And likewise, minus 2 and minus 3 respectively for mu minus 2 sigma, mu minus 3 sigma. Nice. Nice, right? Because if we have some other data sets, right, and they are wildly fluctuating, or some other data sets, they are hardly at all fluctuating. They're bunching up very close to mu. That means the sigma is very small, 0.01 or something like that, right? No matter what, okay, when no matter what sort of data, so whether it is, you know, like this or like this, doesn't matter, right? And the idea is that if your x is some numbers, like mu equals to 107, very differently scaled, right? And each step of the way, the sigma is 25.2. So very wide fluctuations, because it's sigma over mu is about a quarter, right? So 25%. That's just wild fluctuations. But when you map to the z-axis, in other words, don't tell me about the x values. Tell me about the z values corresponding to the x-axis. Then you will get same thing. +1, +2, +3, -1, -2, -3. And you get the idea. No matter what data set we are presented with or we obtain from measurements, right? Doesn't matter about the mu being very large or very small, right? So in this case, mu is 0.01, but we kind of expand the scale. And sigma, of course, will be something similar. Let's say also 0.012. So it's quite scary because it is more than 100% of mu. Can you see that? Yeah. Even though mu is very small, but sigma is about the same magnitude as mu. So that's like a big CV, right? Then what happens when we convert to z value? That means we look at the z value version of the same data set. We get, of course, the mu always maps to 0, and mu plus sigma always gives us +1, +2. Notice that I didn't draw them in terms of normal bell curve. If you're familiar with bell curve, I didn't actually draw a bell shape because it doesn't matter. The z value still applies because the definition of z value doesn't involve normal shape or definition or distribution. It just uses the mu and sigma, right? So it's like a scale conversion. Why is this good? Because any data that lies typically beyond ±3 of z will be considered outliers. Okay, so any data set we can so-called detect or find out about outliers by converting the data set to z values, right? And if you are more sensitive, you may even say beyond 2.5, z equals to ±2.5. Beyond that is considered outlier. But typically ±3 will be considered outliers. That means they are large or they are extremely small. No matter what the scale and average your data is trying to show. So that's the usefulness of Z-graph. All right, so this formula. And very quickly, we can calculate example. Z value for 12 is Z12 is equal to 12 minus 10.5 over 4.7170. That's equal to 0.3180. So we know that the value 12, in this case 12 here is somewhere here, right? 0.31 is around here, less than half. We know that it is quite close to the mean. So long as it's a number close to 0, it's close to the mean, right? And it is on the right side of the mean because it's positive. And it is definitely not an outlier because it's so much smaller than 3. And indeed, that's true. Now, notice that when we calculate this, we may not have the full view of the data. We may just know one value. So that's why from one value, we straight away will know. If we know mu and sigma. See, 3 numbers alone, we can calculate z and infer a lot of observations about that particular data. Okay, so remember when we talk about z value, is towards the direction of skewness, right? So what's so big deal about skewness? Now, for skewness, it is trying to describe. So skewness is a descriptive. Descriptive means it's a summary, right? It's a number that summarizes the behavior of the sample or the population. Okay, so skewness is a descriptive to convey the sense of tailness. That means the stretch of outliers. That means on the left or on the right. Yeah? So if the tail stretches out on the right, then it's a right skewed data set. So for example, we have this kind. Right? So the tail keeps going towards maybe infinity, and over here it is stopping at 0. Okay, so this is right tail because the tail points towards right skewed or right tailed. Right, and also known as positively skewed because it is pointing towards positive infinity. Of course, there's another comparison, the other side of it. It doesn't matter where is the 0, so long as the tail here, yeah, is pointing towards minus infinity, then it is considered a left skewed distribution or data set, or negatively skewed. Positively skewed and negatively skewed also is reflected in the skewness descriptive. If it's positively skewed, the skewness is positive. If it's negatively skewed, the skewness is negative. Now, when I draw a diagram like this, it's easy for you to see and agree with me. Oh yeah, the tail is longer on the left side, so left skew or negatively skewed. Yeah, the tail is longer on the right. But what if you cannot see the tail? What if you don't have the ability or temporarily not being able to see the curve, the entire data set? Then can we have a descriptive to talk about the skewness of the distribution, the slantedness of the data set? That's what we are talking about. That's why skewness gives us this LED light. Oh, it's positive, green light on the right skew. It's red light, oh, it's negatively skewed. Or it's orange, neutral. Right? So perfectly zero skewed distributions will be very artificial, such as the bell curve, normal distribution. They are artificially created to be exactly 0. Real life data sets almost never give you exact skewness. So if you get something like 0.0134 skewness, well, it's positively skewed slightly, ever so slightly, but you can just jolly well treat it as rather balanced. So that's just an interpretation. Now, for population skewness, okay, it's defined as the expected operator. Remember, the expected operator can only be applied to population parameters or measures. Okay, so it is the expected value of the x, the data, minus the mu over sigma, then raised to the power of 3. Why 3? Why not 3.1? Why not 2.5? Is based partly on the ability of raising to the power of 3 shows us this property. All right. You can also raise to the power of 5 or odd powers. Raise to the power of 1 is just the mean, so it's not useful. Raise to the power of 5, that is going to have additional behavior that doesn't just review the tailness, but something else as well. So getting more complicated as we raise the power. So 3 is just right. So in a way, the definition is just to tune it towards what we want. Okay. Now, notice that this is exactly the Z formula, but this is a number, but this is a random variable. Okay, but no big deal. We can also have a random variable version of x, which is just applying the same formula to all numbers in x, in the capital X, in the data set X. So we will get e of capital Z, not the small z. This is a small z, right? Raised to the power of 3. And if we do that, it will give us the population skewness. So what does it mean? Well, remember the expected operator is basically like the average of whatever is inside, which is to say that if we have the numbers all laid out in sequence, then we have x1, x2, x3, x4, xi in general minus mu over sigma raised to the power of cube. And this is the computable formula, right? This is still theoretical, but this is a formula that you can do it on calculator or Excel or Python. And of course, the what the bin versions, as you are now getting more familiar. J equals to 1 to k bins. Each bin has frequency f of j multiplied by the z value of the bin label xj raised to the power of 3. So variance, remember, it is raising to the power of 2, right? So that gives us a fluctuation, and squaring cancels out the negative signs. So example, using the examples here. Where's the example? Example. Yeah, I'm just going to lower myself. Over here, all right, we have the labels 5, 10, 15, 20. And it's a good idea to just convert all of them to Z values first. So xj and Z of j. So 5 converts to minus 1.166. 10 converts to minus 0.1060. And you just apply the Z formula, right? The Z formula. 15 converts to 0.9540. And finally, 20 converts to 2.0140. Okay, and the skewness population is going to be the frequency, right? So 3 times the Z value minus 1.166 raised to the power of 3. And I'm just going to present it vertically down because it's easier to check and compare. 2 times 0.9540 raised to the power of 3 plus 1 times of 2.0140 raised to the power of 3. So the whole thing, right, is to be multiplied by 1 over n. So multiplied by adding up 3 plus 4 plus 2 plus 1, we get 10. Okay, so if your calculation is the same as mine and I didn't mess up, you should get 5.1452 over 10. Answer is 0.5145. So if you do Excel, you will get skew.p. The dot p means the population skewness. You will get this. All right, repeating 5 3 times, 10 4 times, 15 2 times, 21 times, you will get skewness of this, population skewness. Okay, what about sample skewness? So let's draw a divider. Okay, sample skewness. Sample skewness, just like variance we encountered some difficulty, right? Because of the n and n minus 1 adjustments. We want it to be an unbiased estimator, so we adjust the n to become n minus 1. Adjust because, again, we've tuned the formula a little bit just to make sure it fits our purpose, right? Okay, so I'm just going to give it to you, and it is like this. There's a multiplier here, n of n minus 1 over n minus 2. So that multiplier is to be multiplied to one over n. Remember, the capital N goes away, so the sample size is little n. Okay. Summation of I equals to 1 to n xi minus x bar. So it does look familiar, right? Because it is the difference from the sample mean, but not surprisingly, we raise to the power of 3 for the whole thing. Okay, so this is the difference from the sample mean, and then raise to the power of 3. Now remember, when we raise to the power of 3, this can be plus and can be minus. The raising to the power, like minus 1 to the power of 3 is minus 1, right? So it can be that the total sum and then divided by a positive n. The total sum can still be negative. And that is possible, right? Because we may have a negatively skewed value. So this may need to be negative. And then we have the denominator. Okay, so here this version is a little bit more towards tuning it to fit our purpose. So we have xi minus x bar square. Up to here, this looks like a sample variance, but then the n here is not exactly correct. Yeah, so it's more like the n minus 1 comes in. And the whole thing is to be taken with a square root and then raising to the power of 3. Okay, so what is the whole big deal here? The whole big deal is to make sure that we don't need to fall back on mu, right? Because just like in variance, when we calculate sample skewness, the main purpose is likely to because we cannot find out the population skewness. That's why we use sample skewness, and we want to point estimate, right? So we want to estimate. And to do that, we want this estimation to be not over, not below. I mean, it may randomly be above the actual population skewness or below, right? But we want to sort of theoretically have the assurance that it will jump, but it will jump in a fair way. You know, it will be an equal number of times that is above and below. Plus, if we work harder and n gets larger and larger and larger, our sample skewness does converge, you know, in a probabilistic manner, does get closer and closer in terms of accuracy and precision towards the population skewness. Because it is the population skewness that we want, right? We can calculate sample skewness, whatever formula we define, but no point if it is not going to serve a purpose. What's the purpose? The business purpose is to understand the population. So to understand the population, in this case, we want to know the population's skewness. We are unable, can't afford, don't have the time, patience, money, budget, manpower to measure every single point in the population because it's too big. And so we want to do a quick measurement of a few samples. N is small, like 10, 15, 12, right? And can we have a number crunching device like this so that when the number comes out, it is going to be close enough, right, towards the actual number. All right, and if we do more hard work, we should get closer and closer. So that's the whole idea. Okay, so to begin, we have an example. So let's have an example. It's a good idea to convert each of them first. So our xj is 5, 10, 15, and 20. Our xj, yeah, we can do the same. Our xj minus x bar cubed and xj minus x bar squared. More because cube is numerator, squared is denominator. So this gives rise to negative 166.375. And for the squaring, we get positive number. This gives rise to negative 0.125 and the squaring 0.25. Okay. Then we have 15. That gives rise to positive number now, 91.125. And for the squaring, 20.25. Okay, and for the 20, we get 857. Because of the cubing, you can see it rapidly amplifies something that is just a little bit larger. The difference when it's a bit larger, it will amplify it. Right? And for squaring, it's 90.2. Okay. We're going to do this in because I can always do this in a flash using Excel, using Python, using R. But the whole idea is to, slow motion everything just for you to see clearly what each individual component is working. So I'm going to just calculate one part at a time, all right? So this part, so there are three parts, quite easily seen. So I'm just going to call this A, right? And I'm just going to call this part B, and not surprisingly, the last part is the C here. Okay, so let's do it part by part, and it's easier to understand. So for A, right, we have the square root of 10 times 10 minus 1 over 10 minus 2. Okay, that's 10 times 9. Take the square root, then divide by 8. You can do the quick calculation. 1.18585. I'm just maintaining a few more decimal places so that I don't get bitten by lack of precision here, right? So I just keep a few. For B, yeah, I'm just going to do the frequency way. This is not in the summation of j format, right? In the bin format. But you guys get the idea by now, since we have practiced so many times. So over here, it is 1 over 10 times inside. That's 3 times of the cube, right? So 3 times of the negative 166.375 plus 4 times, yeah, this one, the negative of 0.125 plus 2 times the 91.125 plus 1 time of 857.37. Okay, and of course we cut the long story short, use the calculator, you get 54. Okay, and for part C, again, same thing, but we're just going to use the square columns instead. 3 times of 30.25, and it's all positive, right? So I don't need to do the bracket now. Plus 4 times 0.25 plus 2 times 20.25 plus 1 times 90.25. Okay, what does this give us? 22.25. Okay, and then what happens? Well, we are going to just combine it, A times B over C, right? So the sample skewness is A times B over C. So that's 1.18585 times 54 over 22.25. Doing well, I did the C without the cube. So let me correct myself because I just want to show for clarity. So the C is without the cube here. Okay, so but you guys know. The square root, no, it's actually also doesn't have the square root. Yeah, because I'm just doing the inner part here. Okay, so but you are clear, right? What I'm doing. The PB is easy. B because it doesn't have further modifications. The C, I need to be careful. I'm just doing the inner part here, right? And so what I need to do is to take the square root and then cube it some more. Now you really don't want to do this by hand all the time, right? But seeing it done once in your life, I think it's worth the while. So now we just do the multiplication, all right, and making sure that you take the square root of 22.25 and then cubing it. You should get 0.6101. And that's what you get as well. In Excel, if you use the skewness without the dot P, right, skew, SKEW, without the dot P, you will get this number. With the dot P, you will get the population. So this is the kind of calculations that is going underneath, right? And up to power of 3, that's quite useful already for our data analysis purposes. And so I'll leave you with that. Thank you very much. See you in the next video.